So, okay, f0 1 over t is also the smallest frequency that you can see. I have uniformly sampled, and because they are uniformly sampled, I can make orthogonal bases out of that. And so I can write this as matrix multiplication. We will do this this afternoon. So if I say that now my signal is stable, so my impulse response admits a Fourier transform, okay? I can look at the impulse response and just focus. I take only the discrete case and focus only on the circle. And what you have is the frequency transfer function, okay? You have seen this over and over again. You typically represent it in both the plots where you plot the absolute value and the argument of the frequency transfer function. This is a sort of low-pass filter, as you can see, and this is introducing some shifts. What is interesting about this with respect to the other transfer function is that this is now a function. In a discrete case, this will be a vector. And this afternoon, we will see that this is, in fact, is a diagonal matrix, okay? But it's a vector. Before, we had the plane to deal with. And so, okay, let's say I want my output. You know it's coming from a convolution. In the frequency domain is a multiplication. And so my output is the inverse Fourier transform of the multiplication of the two, okay? Which now brings me to multi-resolution analysis and filters, and this will open the stage for the lecture of today on time-frequency analysis. So, well, you know, filters, you have mainly three families: low pass, band pass, and high pass, okay? Low pass means that you have a cutoff frequency and everything before this can pass. Band pass means that you're focusing only within a range, and high pass means that you're taking the upper range up to fs over 2. Of course, there is nothing higher than that, okay? Here I'm writing it as a square. It cannot be a square because otherwise the impulse response becomes infinity, so bear with me, I'm oversimplifying that. But in the notes you have a detailed derivation of finite impulse response filters and infinite impulse response filters. So for the moment, let's have a bit of imagination, and let's say that I can do this really with a very short cutoff. Where is multi-resolution analysis coming from? Multi-resolution analysis comes when I say that I want to use complementary filters, or filter banks, as you will say. So I want that my filters, the transfer function, adds up to 1, okay? If I add more constraint on the filter, I might, for example, ask that I don't want any phase shift, so the transfer function is real, then this is equal to saying modulus of all these things is equal to 1, okay? And so if I can guarantee you that this is going to happen, then I can guarantee you that the three parts that you have identified when you have filtered the signal 3 times are going to add up to adds up to the signal that you originally had, okay? And to guarantee this, what you usually want is to set some constraint on how you derive these transfer functions. For example, let's say that I give you the low pass, then if I want to complement it with this, then I will derive the high pass as 1 minus the low pass, okay? And the band 1 will be the difference between low pass. So conclusion, you only need a low pass filter, and by taking differences, you create all your band pass and all your high pass filters, okay? If you generalize this to a set of scales, in multi-resolution analysis, you will call this scales. What you're simply doing is you're taking your signal and dividing it into some portions, different portions, and these are what we call scales. Maybe you want to isolate what is happening only at this scale, differently from what is happening at this scales, for example, okay? And all you need is to define a carefully tuned set of filters to do this. So the summation of scale, here let's say I take m scales, is a summation of inverse Fourier transform of these guys. And all I want is that this transfer function are approximately 1 within the range that is their range of competence, let's say, and are 0 anywhere else. So that transfer function will tell me what is happening at that scale, okay? We will use this to constrain POD this afternoon, okay? So all you need is to define, and I wrote a little Python function on the nodes where you give to him a frequency splitting vector. So you tell 10 entries, and he will split your signal accordingly. Okay. And what it will do is basically a cascade of low pass. So I create a low pass filter, and I subtract to create the band pass, and so on and so forth. Now, in wavelet terminology, this will be called scales, and these will be called details or wavelets. But this we will see it this afternoon. Okay. So this is the exercise that I gave you. So you have a signal, which is this one, which is constructed by 3 harmonics plus some noise. They have different frequencies. They are modulated by Gaussians. So let's say this one, you have one that exists only in this range, another that exists only in this range. It's really noisy. You do an FFT, you see that you have 3 frequencies, 1, 20, and 90. And if you limit your analysis to frequency, you cannot tell me when this has occurred. Okay, if I ask you, yes, you have 20 hertz, but when did this 20 hertz occur? And this is the lecture of that will follow. So in this little tutorial, you see I start by, I'm not going to do a Jupyter notebook, sorry for that. I'm not that good as Professor does in Python. So this is a shameless print screen from the nodes. Okay. So you load your data, you define your three parts, you just sum them up, you add some random noise. And then you call a function, the function that I gave to you. Here I'm using a scaling like this. I have 10, 70, 110, and 300. It means that I want to isolate everything that happens from 0 to 10, from 10 to 70, from 70 to 110, and from 110 to 300. And everything else can go together. I mean, I don't really want to split them. And then you call this function, which takes as an input just your signal, this vector. You just have to tell the function what is the sampling frequency, and this is the order of the filter that you're going to use in your multi-resolution analysis. Okay. If you want to look at how this function looks like, you just have, okay, you take these inputs, you initialize a matrix that has along the columns all the contribution of the scales, and it's going to have nm columns. That is the number of scales that you want to isolate. And then you have a loop. I ask you to have a look at the codes, but you see a lot of this 1 minus, 1 minus, because I'm creating the cascading of the filters. And you collect in the output something that looks like that. This is the transfer function of the scales that you have defined to isolate what is happening in the different steps. And this is the results that you have seen already before. So you isolate a very large scale from a fine scale, this one and this one. And what is particularly interesting is that you have also time localization, because you did that through a filtering. So you can say that this particular range of frequencies is mostly occurring somewhere around here. Okay, this was noise, and you have something that occurred at that specific location. That is the mixing between time and frequency analysis. Questions? Okay. We have? Yes, there is one. One each. I think we have 2 microphones. Maybe you can ask it simultaneously. One at a time, but I already can give you the microphone.
Slightly convoluted question, actually, but could you also do a wavelet transform to get a similar kind of result, or
to get the
a wavelet transform?
Yes, yes.
Yes. Could you do a similar sort of thing? Would it give you a similar result?
I tell you a secret. This is a wavelet transform.
Oh, okay. Well, no.
Okay, this is exactly a wavelet transform. Okay, the way you will see it is to do it in the time domain. But I don't know if you're familiar with wavelets and the discrete wavelet transform, the algorithm from Mala. Basically, it's taking this transfer function to have a special property that they have to be divided by 2. So you take your spectra, you divide it by 2. And then you take the small guy, the large scale part, and you divide it by 2 again. And then you divide it by 2 again. Huh?
You're spoiling.
I'm spoiling, sorry. You're right. It will come. This is a wavelet transform.
You are beautifully teaching the art of linear modeling. Suppose I give you an exercise. I give you some inputs and some outputs, and you have to tell me if this input-output can be characterized by a linear system or not. Do you have something like a red flag where you would say, okay, the approaches are not applicable, or could you have something like a red flag where you would say the data which I get, the input-output data which I get, is not enough to answer this question?
Yes, that is an exercise that I already gave to my. I don't know if I will ask my student to reply that. Maybe he's hiding somewhere. Well, I will use simply, I don't know if you've recognized that this is a sort of Armax model at the end. I just don't put the noise, not to scare people, but this is an Armax model. If you give me hundreds of these guys and hundreds of these guys, you can build this in a matrix formalism, and you can solve a least square problem. And this least square problem will give you a solution on what should be the A's and the B's. Now you plug this back and you check the error. If you have a big error, then it means that 2 things. Either you did not put enough terms, or simply the problem cannot be described by a linear mapping.
Or there's a more likely thing that the thing is numerically ill-conditioned. So when I see the things the coefficients which come out from a straightforward least square things, they look pretty random. So you need to have some extra smoothing on top.
But the
for experimental data.
Yeah, the error. I mean, the error should tell you. If I will do that, if on experimental data,
and it should be smooth. So, I mean, they should be smooth, and this is so it's a bit more than a root mean square problem.
It has to add some frequency constraint. Is a least square problem on smoothed data in a way. But let's say the tools are these ones, the one that I will use at least. Another question? If not,
I have a free microphone.
Okay, so you've seen this part, and now what is next? I think I will close this lecture a bit ahead of time by telling you that everything you have seen today about the comparison process, that picture of this projection that you will see it this afternoon at least another 4 times. Is going to be really the essence of model analysis, in fact. If you do a POD or a DMD, you compute a basis, and then you ask yourself how much your data looks like that basis. Okay, and as Professor Jimenez was saying yesterday, there is no perfect basis. I mean, there are different ways of representing the things. Then it's up to you. There was a question yesterday: when should I use the DMD or the POD? Well, that depends on what is the question that you are asking. These are tools to take a data and project it onto a different basis. Is this basis better than the other? It depends on what you want to do. If you want to do compression, then probably POD is 99% of the time the best, okay? Because you want just few modes, so you want to find a basis such that only few guys matters, let's say. Okay. If you want to do analysis, like continuous wavelet analysis, but I will not spoil too much, promise, then you really want to have the opposite. You really want to have a lot of vectors because you want to compare your stuff with many things to see when something is occurring or not. Okay. So it's all about perspective. These are tools to look at the data from different views. Okay. So I think this is enough for the moment. In the multi-scale POD, we'll talk a bit more about that. The multi-resolution analysis, as I said, is already an introduction to the wavelets, and this afternoon we will see how to combine this idea to the POD, to have a decomposition that is somewhere in between POD and DMD. In fact, it can move from one to the other. And the notion of linear dynamical system and control, basically, I started already talking about that, but tomorrow Professor Dawson will talk more about linear dynamical system and control in a different perspective, which is the state space representation, where let's say you're less scared about MIMOs, because otherwise in MIMOs those guys will become matrices. But let's say that is a perspective that is slightly, I mean, it's better, it's more suited for that. So what I try to do is, I took all the textbooks that you have in high school on signal processing, orthogonal transform, and things like that, and I try to see what kind of answer I can find from these undergraduate courses that are actually existing in these more advanced topics that we are covering today. And I also mentioned a bit about feedback control and feedback and feed-forward control. So I guess the last answer is the exercise that is solved. There remains this one to answer. I guess I mostly did, but well, if you have more questions concerning these points, we can discuss them over a coffee. Okay. So I think that's it. I thank you for your attention. And we have 5 minutes for questions, if you have.
How do you think your lecture will change in the next 10 or 20 years? And it sounds like a funny question, but I assume a lot of the things which you have presented will be part of some software packages, and so people will move away from trying to understand a lot of the difficult linear things like a Fourier transform and so on, and instead they will just use some MATLAB code, some MATLAB commands or something like that. So.
That's a very difficult question, in fact. Well, I hope nobody will just use a MATLAB code or Python code without knowing what is happening behind the line. This, of course, is the responsibility of the instructor to avoid this, I would say.
But the instructor may know.
I will say that this kind of material will be given earlier and earlier and earlier in academic courses. And this will be, let's say, not replaced, but complemented. We will spend more time on non-linear problems. We know already everything about linear problems.
But it always comes at an expense. So I was in an MIT workshop, and we had a discussion. So everybody says the student has to learn more, but to some extent the capacity is limited. So the idea that you can increase the curriculum by a factor 2 is illusory. So at some point you have to say, for instance, in Berlin we had the discussion the students should not learn Navier-Stokes equation and potential flow anymore because there is a fluent solver. I mean, this was a ridiculous suggestion. But but to some extent, then there are other people who say, I can actually increase the volume, what the students can learn by making better and better courses. And some people dedicate essentially their life now to having web-based interactive curricula where the students can learn things much easier, and probably from there you can get a factor 5, but it requires people who are really dedicated. And it's not really clear that these web-based courses with a lot of visual interactions actually teach better. They give the students a feeling of learning more. Yes.
But of course that is a solution. In a way, you're right that the more we advance, the more things you should put in the curriculum, and so at some moment this saturates. But we also have more tools to explain them better. I think if you try to balance a bit practice with theory, this should help. Where is really the saturation up to the point where you have to remove something like potential flow or things like this? I guess I'm too young to answer this question. This is a question for you, I mean, for senior people.
For me in 10 years.
Okay.
I hope I have some more years.
Do we have other questions? But then if not, we can go to have a coffee, I think I would say. Okay. Thank you.